Hello everybody! Welcome to Functional Forever! Today we're going to be porting the zipper exercise, which we looked at the other night, and I didn't even realize that it's implementing the zipper data structure, which is like, I'm actually like unreasonably excited about these things. Okay, so just getting things set up here. And here is the exercise generator. So I already connected it here. Define the slug as zipper, and let's see if it pulls it all right. And it looks like it did. Now we just stored our data, the canonical data, the description, and the exercise metadata. And here we go. Let's see. This function is supposed to initialize the depths. And, let's see. I haven't actually gotten to the point where I can just run the script in one shot to create the thing. So, of course, I'm not completely confident that this is going to totally work. I mean, especially because, yeah, I know that the test suite for Zipper is way more complicated than the one for Yacht, and that's actually the primary reason why I am doing this. So, is to make the generator script more generic, so that it'll work with more exercises. Let's see, init depths, which takes, does it take the entire data or just the canonical data? I think it's the canonical data. And yeah, let's see, we got an error, which we never get any of those. Let's see what happened. I can try to just evaluate this here. Oh, I guess that is the problem. Oh, you know what? I actually lost some work, unfortunately. But it's okay. Because, yeah, I think I remember having to do this last time or something. So, yeah, now exercise data now needs to be exercise of canonical data of the data, and same here. So now let's see if it works. Nope. All right, so how about just this one? Nope. All right, let's see what's going on. So the FS path, oh, that's not even evaluating. What is this? That's returning nil. Why would that be? What's the canonical data? Okay, this is right. Okay, let's see what we have at the top. Exercise. Oh, because we're not, yeah, I forgot to put true here. We're parsing the string from the JSON, and then we need true so that it will turn the string keys into keyword keys. Let's try it now. Oh, no, still something messed up. Let's see. Let's try that. Oh, okay. And there's our directory. Cool. That created the zipper directory and the source directory inside of it. And now, let's see, we'll have to figure out what would be the problem with this. No, oh, I guess it, oh, so why didn't it work before? Okay, so now we have the depth-seeded file, which is great. Now the slug is going to be canonical data of data. As is this. And I will evaluate that, and then we'll say init line. And that didn't work. Let's figure out why that would be. fs file. Exercises practice zipper project CLJ. Yep, that's correct. So we're spitting that, and it's going to be this string. Yeah, why wouldn't this work? Let's say the exercise is zipper. Yo, what's the problem? Oh, you know what? Wait, no, that's this looks totally fine. Let's see what we defined slug as zipper. So let's try evaluating this. And yeah, okay, this is if that's fine and that's fine, then yeah, I don't know why this wouldn't work. Guess I have to copy the body out and try to debug this step by step or something. So the exercise slug I'll comment out the whole body, and then we can just do like some confidence checks. So we'll just output the slug. That's zipper. Yep. Okay, now what else can we check? Maybe... No, that doesn't make sense. I can't see any reason why this wouldn't be working. Exercises, practice, zipper, project CLJ. Yep. I already checked this. This is the string that it will output. And yeah, so why why wouldn't this work? I think maybe it's time to stop using computers forever. But okay, now it worked. Okay. I didn't do anything. Wow. All right. Well, there it is. I have no idea what happened there. Let's continue. That'll get our test. Oh my God, stop it. Freaking assholes making noise. I hate that. Testing forms, def test forms. Okay, this is gonna be fun. Init tests. Okay, so this is the most involved part. Init tests takes. Yeah, so like, I'm gonna have to change all of these, I guess. Right? No, we can just pass canonical data to it. Huh, that actually... Okay, well, we have some sort of test suite. All right, wow, that's... I wasn't even expecting to get anything back. So let's see what we've got. Expected value test. And same result from operations test. Huh. This is crazy. I can't believe it actually seems somewhat sound. Okay, we need to open up the canonical data in a way that yeah, you know, I'll just evaluate it here so that it will be in the bottom window here. Cool. So now we can go through this and see. You know what I want to do is actually I want to not assume that anyone knows what zippers are, actually, because they are really cool. I had no idea there was a zipper exercise on Exercism. It's like... So yeah, we've got, let's go to the exercise. And we'll have to go to like the JavaScript track or something. And let's see. I'm actually thinking I want to stand up. So I have this really cool adjustable desk. So if you pardon me for a moment, I am going to do this. Once I I just messed up the camera. Okay, I think that's right. All right, now go. Okay. I think I'm gonna get my kitty cats this week. Oh my god! They're gonna be so cute! Oh, you just wait. It's gonna be the cutest kitties in the whole world. Alright, is that good? Yeah, that'll do it. Let's get rid of this. No more chat. Okay, I think that's probably right. I need to move this up a little bit, and this will cool. All right. Oh, whoops. Okay, space age. Zipper. Okay, creating a zipper for a binary tree. Zippers are a purely functional way of navigating within a data structure and manipulating it. This is what we've used. We use it in the Clojure test runner, and we use it in the representer, which I pretty much developed the whole representer while on stream. It took me a long time to figure out how to use them. And then, but once it clicked, it was just like, wow, really cool. They essentially contain a data structure and a pointer into that data structure. Here they call it the focus. In the Clojure implementation, it's called a location, or a loc for short. For example, given a rose tree, which I've never heard of a rose tree, where each node contains a value and a list of child nodes, a zipper might support these operations. So from tree, but actually before I even go on, I want to So the zipper was described by Gerard Huet in 1997. It's like a fairly new thing. And yeah, let's actually look at the paper. Functional Perl, the zipper. I think the original implementation was in OCaml. Almost every programmer has faced the problem of representing a tree together with a subtree that is the focus of attention, where that focus may move left, right, up, or down the tree. The zipper is Huet's nifty name for, I don't know if I'm, whatever, for a nifty data structure which fulfills this need. I wish I had known of it when I faced this task, because the solution I came up with was not quite so efficient or elegant as the zipper. And it actually just gets right into explaining the navigation primitives, which we basically saw over here. Okay, so maybe we're ready for this. I don't know. I guess we didn't really get much out of that, but I don't want to get stun locked on the paper any more than necessary. So from tree would be an operation to get a zipper out of a rose tree. The focus is on the root node. Let's check out rose tree. Let's see what we, yeah, not a rose, literal rose tree. So let's see, in computer science. Yes. Oh, okay, it is a thing. It's a thing, it's a thing, it's a thing. Okay, a rose tree is a term for the value of a tree data structure with a variable and unbounded number of branches per node. Okay. The term is mostly used in the functional programming community, like in the context of the Bird-Mertens formalism. Apart from the multi-branching property, the most essential characteristic of rose trees is the coincidence of bisimilarity with identity. Two distinct rose trees are never bisimilar. So this is a hard exercise. Might be harder than any that I've actually attempted before. But there's ways that we can probably cheat, because we have, as we know, an implementation of zippers in the Clojure ecosystem itself, written by Rich Hickey. And we might take a look at it, except it works using metadata. So we know that that's some way to do it. I'm curious if there's another way to do it without metadata. Imagine there is, but so the rose tree would be like, just, I don't know, like a hash map, just like a regular like JavaScript object or something. And then it would, so from tree would like zip it up. Okay, and then to tree would get the rows tree out of the zipper. That makes sense. Value gets the value of the focus node. In other words, yeah, the part that is currently the focus of attention. And we have previous and next, which is what in Clojure they're called left and right, which is actually kind of like, that's like a Western bias, because left to right reading languages, it's intuitive for us to think that things go left to right, but that's actually a cultural thing. Okay, so previous is to move the focus to the previous child of the same parent. Returns a new zipper, and then next goes to the next child. Up moves the focus to the parent, returns a new zipper. Set value, so that's like to edit a node. Set the value of the focus node, returns a new zipper. I can't believe that Exercism has this. This is crazy. Insert before inserts a new subtree before the focus node. It becomes the previous of the focus node, returns a new zipper. I'm having trouble visualizing that, to be honest. And likewise, insert after inserts a new subtree after the focus node and becomes the next. So it's just like, okay, so would that take like another tree and it just kind of like sticks, like transplants the whole tree system in the other tree, I guess? And delete removes the focus node and all subtrees. Focus moves to the next node if possible, otherwise to the previous node if possible, otherwise to the parent node, returns a new zipper. All right, so let's see. Wow. Let's look at this exercise here. I want to take a quick glance at the JavaScript solution. Even though, like, who made this exercise? This is crazy. Can probably find out. Actually, I think that is in the exercise config JSON, which is in the meta directory. Matthew Morgan. And these people contributed. In problem specifications, there is a file called Metadata toml. Oh, so yeah, that's just a title in the blurb. Okay. So let's take a good look at the canonical data again. I'm very skeptical that we actually got everything because, well, I was not that careful when I was doing the generator. So for each input, let's take a look at what we've got here again. this is supposed to be the expected value. Let's see. Maybe I will just that's kind of cool. Okay, so this actually looks right. This like this looks good. How did that do that? I guess it just turned the JSON object into a Clojure map, which is all that we needed. I thought this was gonna be so hard, even though apparently it was not. The hard part is yet to come. But wow, this actually looks like it looks really good. Operation to tree. Is that what it's supposed to be? So let's see what we've got here. Way up to the top. Okay. Up to the top here. So yeah, the test cases for this exercise include an initial tree and a series of operations to perform on the initial tree. Trees are nested objects. Each node has a value left and right. Value left, right. Value tree. All right, so data is retained. This is the property being tested is expected value, so which is the def test form, and the input. The input is an initial tree. All right, so here. I don't see initial tree anywhere. Which is interesting. Shouldn't we see type tree? That's input. Okay, yeah, the expected value is first. And so that's the expected key. Okay, yeah, so that's right. The type is tree, value is 1, or value is another tree. So with a value of 1, that has a left tree and a right tree, which are this and this. Left, right. Okay, wow. Then, okay, so then the call to zipper expected value. Oh, you know what? There's still no initial tree. Initial tree. Huh. So let's see what the test suite looks like in JavaScript. that will that'll be easier to help figure this out. Actually, it was in here, I think. Yes. Proof. Wait, this is that's the solution. Huh, that's actually not that complicated. That's and that's JavaScript. Wow, that's like that doesn't seem well, just because it looks nice and concise doesn't mean it was easy to do. Okay, where is the oh yeah, it's called Spec. Zipper Spec. So a binary tree is just like a function that takes a value and left and right and like turns it into an object or something. And then there's a leaf, which returns a binary tree, which is yeah, a leaf node, so that the children are null. That makes sense. All right, so it defines a bunch of trees. Where is the initial tree thing? This actually doesn't seem that complicated, and I'm shocked to see that it seems like the test suite ported over just fine. No, it doesn't say initial tree anywhere. Like, what happened to that key? It was in the canonical data. There's that's yacht. Oh, there's Clojure core. We don't need that right now. One of the inputs is called InitialTree. Actually, that is the inputs are InitialTree and operations. Okay, and operations is just it's an array. So let's see what we have over here. So the inputs yeah, so that's the first argument is the initial tree. Huh, yeah, I guess amazing. So we generated the stub file, right? Wait, no, we have not. We still need to play around with this. We have init src. So let's try that. And that's going to take canonical data. And I think that, oh, it didn't work. Because yeah, actually that should be fine. Oh, you know what? Wait, no. Let's see what this returns. And yeah, that doesn't work just because I'll just fix this here. Exercise canonical data of data, and likewise here. And now if I that's the file name is exercise practice zipper src zipper.clj. Yep, that the file name is correct. So the source NS form, and that's being passed canonical data of data. I think that's what it needs to be. If I evaluate just this, yeah, so that's the namespace there. And there's something over here that's probably similar. Cases data needs to be cases canonical data. All right, I'll just try running this now. Oh, and it didn't work. Let's see what else. Let's check out the source NS form. Wait, I already did that, right? Yeah, and that's correct. So let's try just this one. Oh, and that also worked. So what's the problem? Oh, because this needs to be data now instead of it. Boop, boop, boop. All right. Wait, no, it's not there. Okay. Yeah. That's what it should be. Isn't this like what it was doing before? I feel like somebody's messing with me. I feel like... Okay, let's try just this. Nil. Oops. No, it's still not there. Why wouldn't it be there? Zipper. Come on, let me see the whole thing. I guess I need to make the font a little smaller. Yeah, I already checked this. Everything is right. What's Come on, where's my file? This is annoying. I don't even care. I'll just make the file myself. I don't want to do this now. Let's say zipper.dlj. What? Overwrite flag it already exists, but where is it? Oh my god, somebody is messing with me. Refresh this. Okay, it's there. Oh my god. VS Code was lying to me that whole time. Oh my god. It's like not showing up, and yet it's there. Ugh. Like, here I'm like going crazy. Something's wrong with my code, and the code is fine. All right, so good. We're ready to go now. Now that I'm pissed. Okay. So what do we need to implement first? Well, expected value test. The data is retained. So we're going to be calling expected value with this tree. So I will copy this and put this in a comment block down here. So that's our initial tree. And the operation so why is this in an array? The second argument is an array of objects or something, or in Clojure we would call it a sequence of maps. Wow, I've been streaming for like 48 minutes and feels like I haven't even done anything yet. Wow. I don't know. But yes, why is it that this is a sequence of maps? When let's look at the instructions again. It says fairly little. Let's see. Might support these operations. Let's see what we get over here. This is a skeleton file for the zipper exercise. This is a class with a bunch of static methods. That's not too bad. It's like the class constructor, and we have the from tree and to tree. So our initial tree is, I guess, our rows tree. So we need to be able to call from tree on the zipper in order to get a zipper. binary tree. Before each, where it calls from tree. Let's look at the answer in JavaScript. From trail. What from trail? What does that mean? From trail takes a tree and the last, I don't know what last means. Rebuild tree. So if the 0 element of last is left, then we return the first element of last as the value, and the left node is the tree. And the right node is the second element of last. And let's see, you know what? I need to take a bathroom break. So I had a bathroom break thing here, but it says starting soon. So I'm going to duplicate it and call it starting soon. And then I'll go back to bathroom break. Wait, seriously, it's not going to let me edit it? What? Why can't I edit it? Because I'm streaming? I can't edit stuff while I'm streaming? What the? Really? Oh, okay. Yeah, I can. Okay, this one is called, bathroom break. All right, I'll be right back. All right. So let's check out the Clojure implementation. I think it's probably time. Clojure zip. Yeah, I opened this up last stream, I think. And I didn't even look at it very much. But okay, so that's the entire library. It's just well, it might not be. Yeah, this is just the Clojure repo itself. And then here we have like Clojure walk, we have Clojure XML, and we have Clojure zip, which he wrote 13 years ago. So the zipper function is like the low-level one that the other higher-level functions calls to create the zipper. And so it takes 4 arguments: a predicate to tell whether we're on a branch or not, the children, make node is, I guess, a function that will return a new child node, and then the root of the tree. And here is where the metadata, and that's actually like the heart of the entire library, is and that's one thing that one of the first things I heard about zippers in Clojure is that the source code is a wondrous example of the use of metadata. And so the keys in our metadata are, well, the 3 functions that are passed in. So then the zipper knows how to tell if a node is a branch, how to return its children, and how to make a new node, so that that information is all stored in the zipper itself. That makes a lot of sense. And so here's one that would return a zipper for nested sequence, for nested sequences given a root sequence. And here we can see how these, like the branch predicate for a zipper for nested sequences, it's a valid branch if it is a sequence. Identity is just the function itself. It's just in other words, to get the children of a node in a nested sequence, you just call the node. I think that makes sense. It's a sequence, so you just call identity, and the children is itself. Yeah, I think that makes sense. And to make a node, we have a function that takes a node and the children And we're putting metadata we're putting the children metadata on it. I want to see like how just that much works. But I guess let's just continue. So then for nested vectors, a branch is a vector. That's how we know that it can have children. Not necessarily that it does, but that it could. And the children of a nested vector is that you just call seek on it. And to create a node, you just make a vector out of the children. Yeah, that kind of makes sense. This one's for XML, which I'm not going to worry about too much because it's XML. But yeah, so it just can't be a string, complement string, which like complement just like negates a function. And the to return the children of an XML node, well, we are composing a function from the seek function, and then we're getting the node's content. Because an XML node has its children in its content key. And this is how we would create a new node, is that we would put the children in the content key of the node. And how come it gets no metadata though? I guess it already has all of the metadata that it needs. So then to return the node at a particular location, or a focus as we're calling it in the exercism lingo, is that you just call loc 0. So what does that mean? What is so the argument is obviously a function. What calls node? So like this would, and it calls node on a location. It must be a map, or no, it's like a vector. To return a sequence of the children of the node at a location, which must be a branch. Then we first test if it's a branch. And then we call the children function. Yeah, so this gets the children function from the metadata. And then calls it on the, passes it the node of the current location. And if it's not a branch, we get an exception, because you can't get the children of a node if it is not, if it can't have children. Cool. Make node returns a new branch node, which uses the make node function from the metadata, passing it the node and the children from the arguments. Okay, this is like so simple, but it's like I couldn't have figured this out. Well, I guess I could if you gave me enough time. So we have lefts and rights. Lefts returns a sequence of the left siblings or the right siblings, which is just a sequence of, yeah, so there's an L key and an R key that has the siblings on the left and the siblings on the right. Down returns the location of the leftmost child of the node at this location. So why is that down? Leftmost would be like, yeah, I don't understand how that's down. Leftmost child. Up, on the other hand, does make sense because it returns the location of the parent of the node, or nil if we are at the top. So, yeah, this is crazy. We call root, and that zips all the way up and returns the root node, reflecting any changes. Wow. Right returns the location of the right sibling of the node at this location, or else nil. Rightmost returns rightmost. Okay, then we have left and leftmost. Then we have the editing functions. Wow, I'm actually feeling a little bit intimidated, I think. And I think I want to sit down again, as much as it sounds crazy. And, I don't know. To replace a node where we don't change places, but it takes a location and a node, and we extract the path from the location, and then we associate the changed, we put changed true in the path so that we know that something was changed. And what does it replace it with? Oh, it replaces it with meta. It returns a vector with the node. Yeah, okay. I think. To edit the node, replaces the node at this location with the value of the function, calling the function on the node with the args. And so, yeah, edit uses the replace function. It's like the code is so simple, it's like deceiving. It makes you think that there's nothing to it when there is like everything to it. To insert a child is to insert the item as the leftmost child of the node at this location without moving. So that just replaces, calls replace on the location, makes a new node, append child is the same thing, only it inserts it as the rightmost child. So insert puts it on the left, append puts it on the right. We have next, previous and next. Okay. Yeah, so we had left and right. Which left and right refers to going left or to the left sibling or the right sibling of the node. Whereas previous and next use a depth first order. So next moves to the next location in the hierarchy, depth first. When reaching the end, returns a distinguished location detectable via end, the end predicate. And that's how you know that there is nothing else here. Please go home. And previous is similar. Then here's the end predicate, which just tells us if it has this end key. This is so simple. It's like to remove a node. Wow, yeah, that's some code there. And this is cool. This is just example code of how it works, which that's great. Let's so we read yeah, that's the entire zipper library. And we don't even need all of this, like we don't need the XML one for sure. Well, like let's actually, I'm gonna copy this text into my editor and play around with it a bit. All right, so that's our zipper function, seek zip. You know what? I'll just children make node path. The lefts, the rights, down, up, root. Right and rightmost, left and leftmost, insert left, insert right, replace, edit, insert child, append child, next, previous, end, remove. Okay, so that's why it didn't evaluate, because that doesn't even make sense. We'll just get rid of it. Refer zip, yeah, we don't want that either. So here we have some data. Which, what kind of data is that? It looks like infix operations. And DZ, data zip. So that's calling vector zip on the data. And let's see what we've got. So DZ, and this is currently our zipper, which it's very innocent looking right now. It's so simple, but wow. So if we go down, so in other words, right now, we are at the root of the tree. So if we go down, then our location is now the next child. In other words, we went down into the tree, and now this part here is our location. And so why is it just this then? Shouldn't it be like this whole thing? I guess we went down, and it seems like it went down twice or something. So on the left we have nothing, because we're all the way to the left. The parent nodes has been replaced with that, which is the whole thing. Well, it's this part is the parent, and then the parent path, parent nodes, yeah, parent nodes and parent path. There is no parent path. And to the right we have this other thing, which is, okay. It's the plus, and then C asterisk D. So then if we went to the right, then we are at plus, which after A times B is the plus, and then we have, yeah, A times B to the left. That's the parent is the same, and to the right we have C and D. So yeah, that makes sense. Then if we went I hate how it scrolls. Like, I just want to see the code. Go, come on, just like go to. Okay, yeah. Oh, we already are at the left. All right. So we went to the right. Now we'll go to the right again. And the current location is now this C times D vector. A times B and plus are to the left. Parent nodes, parent path, and there's nothing on the right. Then if we go down, then we just descended into this vector with C times D, and we are now at C. There's nothing to the left. And now for the first time we have a parent path. I think that's parent path. So the parent nodes are A times B plus C times D and C times D. Why is that also? Okay, I guess because yeah, I think that makes sense. So the parent path, we have on the left this A times B plus parent nodes. Wow, this is kind of confusing. Then we have times D on the right, which sort of makes sense, I guess. And then we went to the right again. Then we're at the star. Down, right, down, right. And that's like editing stuff, which is kind of advanced. But, and here's some examples of how you would do a replace and a remove. And wow, so okay. I'm honestly not sure how far I'm gonna get. Well, they don't call the exercise hard for nothing. But we can just go one test at a time. We just need to test whether the data is retained. So if we have this initial tree, or well, that's what it's supposed to return. So if we call zipper expected value, what kind of function name is expected value? We have this toTree operation. Let's see what it looks like in the JavaScript one. You know, I do need to sit down again. And we go down, 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 down. Meow, meow. Meow, 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 meow. Meow, 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 meow. Meow, 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 meow. Meow, 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 meow. Just wait till I get these kitty cats. They're gonna be so cute. Oh, you just wait. Their names are Gwendolyn, or just Gwen, and their sister Naomi. And they're so cute. All right. So let's see. Need to move the camera up a tiny bit again. Wait, that's the wrong way. All right, let me just show you. I'll show you pictures of my kitties. That sounds like fun now. Let's say I'm getting them from the Ofosa Animal Shelter, and they're so cute. They have dogs and cats. And let's look at cats. Let's see. Wow, this website is slow. Oh, this kitty, this makes me so sad because he got, oh my god, I'm gonna cry. He got he got attacked, and now he has to wear a diaper, and he lost part of his tail, and oh, he's so cute. It tears me up because like I would love him, but I just don't know if I could take care of a cat like where I would have to change diapers all the time. Like I'm like partially disabled. You kind of need two hands to change a diaper. I mean, I don't know. Oh, he's so cute. And here's Gwendolyn. And There's that picture, and oh, these are it's Gwendolyn. These are different pictures, aren't they? Let's see if the foster has no, I still haven't gotten a response back from. And there's a video. You can watch a video. And can I make this like really big or something? Oh no, I can't. Hang on. Gwendolyn. Oh, let's watch it again. There we go. See, this is cute. She does a floppy. She's gonna be a programming kitty. Okay, and then her sister is Naomi. And there she is. They're both a year, 11 months. Oh, and there's Gwendolyn in the background. And he's on the bed. Oh, and now there's Naomi. And here's a video of her playing with string or something. And she plays, and she plays, and she plays. I have to watch it again. It went by so fast. Yeah, boop, boop, boop. Boop, 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 boop. Meow, 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 meow. Oh, okay. I can't wait. Kitties, 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 kitties. Alright, zippers. Back to zippers. Oh. I was really excited about this last night. Now I'm like daunted by how deceptively like it all seems so simple. And that's the way to write library code, in my opinion. Like, so the functions are so small. It's when you're reading it, it's like, oh yeah, that's obvious. Oh yeah, that's obvious. That makes sense. But like, I imagined that there was a lot more to it when I'm using the zipper library. Like, say the functions that I usually call are like well, up, down, left, and right mostly. So like moving down the tree, I'm confused why it says leftmost child. Like, what does down have to? Oh, okay. Leftmost child. Okay, so the children are down, and it starts with the one on the left. Okay, that does make sense. Like, yeah, so like slowly, this is gonna start making like little bits of micro sense. So yeah, like I imagined that it was like doing all sorts of crazy stuff. Like when I called like down. So when you called down, let's try to call these. Okay, let's try to figure out what's the first thing to test. Binary tree. So a binary tree is like we're gonna let's see, let me think. It's gonna be represented as a hash map, but does that even make sense? Like the vector zipper represents the same tree, but just implicitly. Like, but the zippers don't, as far as I know, use hash maps. Let's check out the Clojure zipper test. Okay, so the first thing is that we take this and call to tree. So what are some of the other operations? Let's go through more of these tests and we'll see. All right, so that's what some I think something is not right. Testing. Why is this the linter is yelling at me? I think it's just because the well, let's find out. We'll go to problems and tell me about your problems. The yacht test, yeah, we're not even working on that right now. Okay. Expected value. Yeah, I think we can just ignore those. Yeah, because it's because we haven't implemented this yet. But expected value is going to take two arguments. It says so right here. So it's going to be a map which is actually called InitialTree. How do I know that? Because it was in the canonical data. So I will put this here. I'm so confused about the names of these functions. Like, and that doesn't, I think that doesn't make sense. Or wait, no, it does. I think it does. We don't have any expected value function here. Yeah, I think the generator is, I don't think we can trust what it actually did. We got like some weird, because I think I made an assumption when I made the generator that that the property was the function name. Okay, like for yacht, the only property that we were testing was the score function. And so I made the mistake of thinking that property means function, the function under test. And I think that's not true, which is why, yeah, it doesn't make any sense that we have expected value. That's like, no, like that's not even right. Now let's, we're gonna have to take a step back. I might have to actually like figure this out off stream, when, I don't know, I actually, truth be told, like I started streaming because it was the only way I could get myself to do anything. Like to, hold on, the camera was slightly off center. It was bothering me. Yeah, so I've been thinking like, if there's like certain qualities that you would expect to, that would cause one to be predisposed for being a good streamer, you know, you could imagine the personality traits that would contribute to that. I am not those things. But, you know, I asked this question in one of my Discord communities the other day, and I got an interesting answer. And they said that sometimes people who are excellent, like public figures, are not they're not enjoyed for their public speaking skills, for like, but rather for their authenticity, which I care a little too much about authenticity, if anything. But it's kind of funny though that I do this simply because it's so unnatural. And it's gotten a lot more natural, I can tell you that. But like, even though I used to play with video cameras when I was a little kid, so you would think that, you know, and also I like played in bands since I was like 16, and have done probably hundreds of performances, like open mic nights, concerts, stuff like that. Yeah, I bet it's hundreds. So you would think that I wouldn't like completely freak out. Like, I started doing this like about, well, over a year ago, I think, was when I started. At first I was doing a little bit of game development stuff, you know, except to say that it would be like insulting to actual game developers. But oh my God, like I could not even, like, just the thought of talking to the camera just made me feel like stupid and ridiculous. I was like, what? Like, no, I'm not going to do this. No. I mean, a lot of it too is like, I still spend like a lot of my time streaming to an empty room, which is objectively weird. Like, but I mean, I just do it because what else am I gonna do? But yeah, like right now, I'm talking to no one. Someone might watch this in the future, but for some reason, I'm still talking. You know, I don't know what I was going for there, but yeah, this is not right. These are not functions. We have, and this test, this is not a function. Well, I believe something there, or it's going to be the operations are, and this is where, so like, I guess I can't really assume that the problem specifications are like in a that there is a coherent spec that they all follow. That might not be the case. Let's see what we have. So yeah, the property being tested is expected value. Input and operations. Let's read this comment again, I guess. An initial tree and a series of operations. Okay, so that is why it is an array. That it could be like a pipeline, as in a series. Yes, series of operations. Like, okay, so yeah, all right, okay, so this is what we are actually calling is left, then right, and then value. Okay, so this is making more sense. So let's go back to the generator. Yep, we got to go back to the generator. Back to the generator. I'm a little zipper. Meow, meow, meow. Here is my meow, meow. Here is my meow. Meow, 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 meow. Zip me up and... oh, no. So, the testing form is gonna be like something totally different. Now, like, let's see what... First of all, let's generate... I'll output some data. We'll say, put a comment form here. And I'll say, let's look at our canonical data. Actually, I just want to look at the cases of the canonical data of the data. My favorite character in the Next Generation was Spot, Data's kitty cat. Meow. Well, you know, the video where Data cries because he missed his kitty. Oh my god. Oh my god. So here's our cases. Let's just look at the first one. So yeah, it's a series of operations. I think we can still leave the testing or the def test. That will be the same because it's still two different properties that are being tested, which I think it makes sense to group them that way. So we will still have expected value test and the other one, the same result from operations test. Because there have been discussions about this, like on the Clojure forums and the Slack channels, about testing strategies, and I don't really remember, but I vaguely remember that, well, there's different strategies that you don't necessarily have to test have a one-to-one relationship between your functions and your test definitions. Let's see, did I just... Yeah, that's just the first one. And the only operation, so we have a function called toTree. Let's just write that. So, hey, look, we're coding. I'm not just looking at kitties and crying. It's a defin toTree. I'm resisting the urge to get rid of that underscore and replace it with a hyphen until we're all done, like I did with the yacht exercise. Meow, 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 meow. Meow, 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 meow. Meow, 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 meow. Sit me over, pour me out. Molly puts the kettle on, and all the tea. Grandma used to sing. In some ways, our tastes change in so many ways, but to the pot we cling. Now I'm a little... I had that record when I was a kid. I've never heard anyone actually like know that whole song. But all right, so we have the toTree that we are testing in this thing, and that is going to be the expected value. So that much is correct. We're not like completely out of the ballpark, but we're just going to call toTree. That's it. I'm like, I'm suddenly very excited. toTree. Okay. Yeah, we just call toTree on that. Yeah, whoop-de-doo. Yeah, that's right. Good. Next, let's go to... Where was I? Yeah. Let's go nth, so we could like do it in order or something. That was the first one, and this will be the second one. So now we have 3 operations: left, right, and value. So we can write these function stubs as well. So we have to tree, which will take a tree. Wait, no, a to tree actually takes a zipper, right? Because like the no, because that is, wait a minute. Is it actually just returning the same thing? To tree. First of all, I need to format this better. Okay. No, these are, wait a minute. Okay, no, that's right, is a tree, which is over here. Two, yeah, these are the same thing. It's just my eyes are playing tricks on me. To tree. Let's see, what is it saying the problem is now? To tree is called with two args. Wait, where is it? How is it called with two args? That's just one. Wait, that is actually okay. So we have no input. There's no input key. Wait, hold on, that might not be correct. Yeah, there is. Okay. Left, right, and value. So the initial tree that it takes. Okay, so this is the first one. So the expected value is, and yeah, we determined that these are the same thing, and that indeed the description of this test is just that the data is retained. And okay, so to tree, what does that tell us? That is, I don't get what. Let's read the instructions again. This one is like kind of a doozy. It's a doozy. To tree is to get the rose tree out of the zipper. But yeah, this is what I don't understand, because is the zipper represented the same way as if we're calling to tree? Wait, I want to look at all right, entire canonical data. I want to look at the comment again. Trees are encoded as nested objects. Yeah, we know that. Each one has value left and right. Each operation in the operations list is an object. The function name is listed under operation. If the function requires arguments, the argument is listed under item. Some functions require values, i.e. numbers, while others require trees. Comments are always optional and can be used almost anywhere. What does that mean? Why is it telling us about comments? I have no idea what that's supposed to mean. So let's see what is an example of item, or if there is an argument, and so it's left, right, and value. I can just search for item. All right. So here we're testing whether we're able to set a value, which is what we would call edit in the Clojure zip library. Yeah, so the set value needs to take a value to set the node to. And so item sounds kind of confusing. Shouldn't it just be like arg? But I don't know. I didn't do it. And here is another set value to 5 in a step in a set of operations. And here is one where we are setting the left node, or so set left is another function. And here we're passing it a tree. Well, it's actually a leaf node because it has a value but no children. But what I don't understand is on the very first one, I guess, I'm so confused. Like to test whether data is retained. I mean, we could just make this pass trivially. I mean, if that really is what we're supposed to do, then yeah. And so anyway, why if toTree takes a tree, and why do we have this? Shouldn't, that actually doesn't make sense, because it actually doesn't. When we made the generator, our code looks for the input key And then it just takes every one of these things as a, it interprets it as a, an argument. So the first argument would be this. Ah, yeah. Wait, that's, yeah, the initial tree. Yeah, so that would be, we're interpreting it as one argument, which is initial tree, which is correct. But not really, no. Because we're not passing it to a function that's called same result from operation. Or, I actually wanted the first one. So yeah, the input is just this. Where this is the tree that we start with. And just like, what is that supposed to do? Like, nothing. I mean, I guess like, I don't know, maybe I'll just, but anyway, yeah, the point is that in our test suite, this is wrong. This is wrong, wrong, wrong. It's wrong, wrong, wrong. It's wrong, 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 wrong. So we don't call tree on the operations, silly. This has got to go. It's just not supposed to be there. Let's see. So how do we? Now I'm like conflating like how to deal with the generator thing and how to deal with solving the exercise itself. I have to do both, but it only makes sense to do one at a time. So right now I'm actually more interested in pecking away at the exercise. Actually, I mean, I'm at like 20% as far as like even like just understanding what the hell, like anything. Yeah, I'm at like 20% understanding, where like 100% is like good enough to start. So everything that I'm doing is just trying to get to 100%, which is enough knowledge to begin. So yeah, we're not testing the operations, and since all this test case is just to call toTree on this, then we're done. That's the whole freaking test. And this just takes one argument, and see, that got rid of that squiggly, and now that's no longer a problem. And we can go on to the next test. And eventually we'll probably have to go back, but that's okay. That's eventually we all have to go back. So the second one, let's go over here. Now this is testing the left, right, and value. left, right, and value. So remember, type is a, wait a minute. Yeah, that's the expected value. Huh, interesting. So if it's type int with value 3, we didn't have this in the other test suite. So this one is like totally different. So yeah, the expected value is just 3. And we'll just say just plain old regular 3. Is that good enough? So since it is a series of operations, that's a perfect opportunity to use the threading operator. And so, yeah, and so we are threading. Also, there are no arguments here, so we can use either one of the threading operators. Let's use thread last. So yeah, we're taking this thing and we are calling left, right, and value. And so yeah, this is just as simple as going left, right, value. And then we get rid of this. Let's see. Wait. Yeah, so I guess we need to implement them. So let's see what they look like in JavaScript. Might be my imagination, but it seems like might actually be slowly getting somewhere. Yeah, so this is, yeah, so there's right, and we know that there's a left and a right function because that's how zippers work. We saw that. So, and yeah, so, and they are just null array functions. They take no arguments. You just call them. It's a function of a zipper. So this is because I don't understand objects. I never learned to think in them, and I kind of like it that way, except for when I have to deal with stupid objects. So it's a zipper class. Constructs with a tree and a trail. Okay, so trail corresponds to P path, the P path, the parent path, or the parent nodes. I don't know which one. And so while these are just like static methods or something, so from the tree returns a zipper, and just past the tree. When we call left, if we are already on the left, then we return null. Okay, otherwise, it returns a new zipper with this tree. So the tree that is passed to this constructor thing, God, I hate objects. Like it's. It returns a new zipper with the tree on the left, and then left, this tree value, this tree right. Okay, left. Left value right. And then it puts the trail the parent path or whatever. So I think that makes sense. If, yeah. So that'll work. We will just have a defen left. A defen right. And value? Am I allowed to have a... Yeah, I guess there's not any core function called value. Okay. Wow. All right, so the functions at least exist now. So, yeah, why is this yelling at me now? It says unresolved symbol, but there they are. So what's the problem? And just evaluate this again. I don't know. Why is it? Why are we import? Oh, because it would have to be zipper left. Okay, let's. All right, yeah. Zipper. Refer. Left, right, value to tree. What? It's still. Come on. Okay, I'm just gonna have to ignore it because there's nothing wrong. But, it's called with one arg, but it... Oh, yeah, I guess it is yeah, this is wrong. How, yeah, that's not. What we actually have to do is like, let's make a let binding. And we will call this, let's see. I'll just call it tree for now. It might changes. And it'll be, there's that. That's called tree. All right. Yeah, so now that we have like a function body, we are going to, so like what does that even, if we're calling left, right, and value, like we're gonna have to change this so that these are not just like this. Because yeah, it doesn't make sense when it's because like it's because this is JavaScript and I hate it. I hate objects. It makes no sense. Once again, like I'm actually getting more confused by having to deal with like JavaScript's bullshit. When I might do myself a favor by ignoring this, but there's no going back now. But yeah, it makes no sense for value just to be called on nothing. Because since here, it's like called within the context of the zipper in this stupid constructor. Where I need this translated in like not object speak. So left it returns a zipper with this stuff. So here's where we would use something like Rich's zipper creation thing. So let's just steal this and but we're not going to use it. Well, actually, yeah, it might be all right, so if we take, is that the thing that data is retained? No, it's not that one that we want. This is our tree. And so, yeah, just to fulfill this thing here, I'm going to get rid of this. and we need to make left, right, and value are going to take a tree. That's all there is to it. It's gonna take a goddamn tree. All right. So then we'll take the tree, and now it is actually going to be, and this is just supposed to go here. Doo-ba-doo. All right. Cool. So that's perfect. This is a perfect entry point. So the first function we will write is left. So in JavaScript, it calls the zipper constructor. And so it takes a tree, which is this tree left, I don't understand what left is supposed to do. But if we look at the test case, maybe then I'll be able to figure it out, because so left, right, and value. So the initial tree value is 1. So that's the root. Or like in the first node of the tree, and the root is 1. And then it has 2 children, left and right. And the child node of 1 is 2. Wait. Yeah, there's a 2 on the left. That has nothing on the left. But on the right of the 2 is a 3. Do I need to draw a picture? Maybe, and then, okay, so that was the left of the 1. Then to the right of the 1 is a 4, and that's a leaf node. And then, okay, so if we're at the 1, then if we call left, like, so what the hell is that supposed to do? Wouldn't left, like, that doesn't make sense. Left what? Left and then right. And then the value is 3. So left, right, value, left. Okay, so we're at node with a value of 1, and on the left, so it's sister. Okay, so 1 has a sister on the left, which is 2. And 2 has null for left, which means there's nothing on the left or at the end. But then, oh my god, this is like 1 on the left is. So does that mean that we're going to the left? We call left, so we move 1 to get. It's supposed to be the navigation function, right? Yeah, and then it returns a new zipper. And that's why we're calling the zipper constructor. Oh boy. So what data structure do we want to use? Like the vectors? I guess that's oh my god, go back to nested sequences. Yes, nested vectors. I guess. All right, so let's say that's not the value of tree is, or maybe it is. Let's see. All right. So how do we turn this into oh, I need to plug this in. Meow, meow, meow. Meow, meow, meow. Meow, meow, meow. Okay. I mean, could we make the zipper be the, because it seems like this is like what it wants to, I'll try using the vector one, but because it seems like that's the only thing that makes sense. I mean, there's no like hash map zip. So to call zipper on this, how would we would like represent it differently? Let's see here. Node branch children make node path lefts rights. Down, up, root, right, rightmost, left, leftmost, insert left, insert right, replace, edit. The next ones, we won't have to do that because we're not going to implement like depth first search or anything. And, I'll go ahead and paste these in though. All right. And I will, I should be able to evaluate this whole file. Yep. And so we don't need next or previous, but we do need end, I think, and maybe remove. And thank God that's it. Okay, so all this is here. And so, so left, the left, let's see what left is over here. Returns the location of the left sibling of the node at this location. And that takes it takes a location. So let's see if we did vector zip and where we called it over here, where we called it on this. So that's this is like a vector zip. So we have our data. And why is this quoted? It's I'm not sure why you would need to quote a vector. Why it's vector zip. Let's see what happens. Let's see what vector zip does again. So we're calling zipper with this stuff. So this will be like the toZip function. And I'm actually just like going to simplify this so that it would be so yeah, we won't need zipper anymore. I'll just include this. So this will go here. And okay, so branch is vector. I mean, I could make this work for hash map. But I guess might not need to. I don't know. I guess I'm just I should just keep doing this because I'm very slowly getting somewhere. All right, so children is seek. And you know, since this is known ahead of time, I can make it simpler because we won't have to include this metadata because it'll just be known. So cool. So then make node is this. And let's see. So we what do we even do? We just okay, it returns a vector of the root and nil. So that's it. Cool. I still don't understand what the what was I gonna say? I still don't understand. I don't know what the we'll find out, I guess. What the I'm so funny. What the quote was for. Why would a vector need to be quoted? That's what I need to find out. So we called vector zip. So now I'm going to get rid of zipper now. Bye-bye. And since we know it's a vector, I'm just going to call this zip. Zip, that's all. Wait, no, we're going to call it toZip. No. Yeah, maybe. I'll call it toZip for now, because that's what the test suite is going to be. So I define that, and we're here. I am, hold on. I'm going to not have these here right away. We need left and we need right. Wait, hold on. Not gonna use, I don't think we need rightmost. If I'm not even gonna have root here yet because or up because I'm not dealing with those right now. Ah. All right, that's better. Right, left. Okay, get rid of leftmost. Insert left. Insert right. Replace. Edit. Insert child. Pin child. Yeah. Value, I think, is node. Yeah, that returns the node at the location. Cool. So yeah, this is what I really want to know. All right, that's much easier to handle now. So toZip on this gives us this. So yeah, what did I just do? I need to make a drink, something Yeah, hold on. I need to need to make some more Gatorade. All right. Yeah. Cool. All right, so 2-zip has this metadata on it. I didn't even notice that anyone was in the chat, but I don't think you're still here. But hey, this is technically a hard exercise I'm trying to tackle. And it's a mind bender, that's for sure. Definitely might not be recommended as something that really makes the best viewing content, because it's a lot of like just kind of thinking and being confused. And streaming is funny because it forces you to talk when I kind of believe that humans are basically like phenomenally bad at doing anything while talking, and that's what streaming is. You know, I could actually like, let me put some music on. Oh, you know what I want to listen to is, and that way I won't feel like I have to talk as much, and so that I might be a little more comfortable just kind of zoning out. And what I want to check out is I just found out about this this harpsichord. I'm a huge fan of like old like Baroque harpsichord music, like before the piano, before Bach even. My grandma used to play this tune by Scarlatti, and I even loved it when she played it on the piano. And the one that she played was called 420. It's was Scarlatti 420. I made her look it up and tell me which, and it just happened to be that one. So this is Sala del. I cannot read that. Is that an S? Cembalo Salcaro Sasson, the Handel harpsichord room. And go to S, I guess, for and it's Domenico Scarlatti. And yeah, when I go doo, and this is one of the only tunes that I like that's actually in a major key, and that is huge. Like it took me most of my life to come up with like an intelligent answer to what kind of music do I like, instead of just being like, oh please, like everything, or like, except no, actually the truth is I'm like so picky when it comes to music, it's ridiculous. Like you would hate me if I told you everything that I actually can't stand. But yeah, I'm extremely picky with music. And so yeah, this is it's in a major key, but it doesn't like make me want to punch someone in the face. Why did it not start? Oh, here we go. Ah, nice. Wow, that's strong Gatorade. What's cool about the harpsichord is that all of the notes are the same volume, which I actually really like because it's simple. I can hear everything. I just want to hear all the notes. Like, don't give me like subtle textures and touch sensitivity. Like, just, like, jam the notes into my skull. That's like the pleading face. Please just play the harpsichord. All right, now. So I'm trying to find out why this quote has to be here. Oh, if it's not quoted, then okay, it's so that it doesn't evaluate the vector. All right, that answers that question. So if we call meta on a node, first of all, like, let's call meta on our zipper to show what it does. And here we can see we have I wish this was just a little bit slower. I have the MIDI of this. I almost like the MIDI better because it's like, this is like a little bit choppy sounding. And like because it's a little bit too fast, but then it like lags. Yeah, so we call meta and it gives us all of these, which is our branch predicate function, the sequence function, and then to make a new node, oh, I guess it's not going to go on. But, yeah, anyway, I'll play, I'll put on my playlist, my classical playlist. This is an old slap bass arrangement of the Prokofiev Toccata. And it's slowed down. Like, this is like a crazy fast piano piece, but here we're hearing it like I wanted to be able to actually hear the notes instead of it just being this flutter of notes. Flurry of notes. And it's just so weird. I had a live performance of this by Martha Algerich, and well, I got it was a copyright match, so I had to replace it with this, but I actually kind of like this. It's like it's like that harpsichord thing again. The slap bass, it just like rams the notes into your skull. It's perfect. This is cool. Okay, so what's going on here? If we call left, first of all, we want to replace this with whatever these values here. So are these siblings or children? I guess it's that one. In other words, the value of the node is 1. And it has two children, it has a left child and a right child. So can I just put the 1 here if I want to construct a tree? And then its children, its children go in the vector, I guess. So there would be, do I put nil for the left? Yeah, I guess so. It's so weird. Alright, so that's a nil's on the left. And on the right is another tree. So, which has a 3. And actually that's it. Does that make sense? Okay, just 3, right? Wait, no, because on the right is... Yeah, I guess that is right. Not on the right, we have a 4. No, it's just without this. Just a 4. I think that's right. Okay, so then if we call left on it, we get nil. Which makes sense, we can't move to the left. What if I call node? Actually, yeah, that's right here. Alright, so yeah, actually, the location wasn't 1. Let's go down. All right, yeah, so then we have 1. Then we have nothing on the left. And the parent nodes is the root. On the right, we have 3. Yeah, nil, 3, and 4. Let's see, where's... I need to get the down function. There's down. Returns the loc of the leftmost child of the node at this location, or nil if no children. I need branch and children. Yeah, that's here. So if the definition of branch is whatever is the branch in the metadata, then what I'm going to do is just get rid of it and get rid of the metadata. And we're, instead of the branch, we're just going to use vector. Yeah, so this is just vector. Yeah. That means I can get rid of this. Now, the children function is seek. Cool. Alright, so when do we use the makeNode function? What I'll do is just call this makeNode. I'll make my own function. Is there one down here? Yeah, okay. Yeah, so, never mind. MakeNode is going to be something like this. So down, MakeNode. So, yeah, if it calls that on node and children, then I can just the loc is only used to supply the constructor. Okay. Yeah, which is that. this is actually all we really need. But, right, so... What calls make node? I see if, Oh, okay. Alright, now... So that's the simplest function I've ever seen, really. To zip just puts it in a vector. That's it. Nil tells us that we're at the end, right? Okay, so if we are here, that should be where we're supposed to be at the beginning of this test here. So we take the tree and then we go left. So let's see what happens if we go left. We can't. Yeah, because if we're at 1, unless the meaning of left in the JavaScript one is like the left child, let's see. So T1 is this. So it's calling BT. This is another one that I like the MIDI file better than listening to somebody actually play the tune. Especially with Chopin. Chopin often has pieces that speed up and slow down. And they like always like over exaggerate the slow part and often play the fast parts too fast. Like you just need to chill out. Just like so that's what the MIDI does. To the left of 1, yes, the left child of 1 is a tree with a 2, nothing on the left and 3 on the right. Yep, that's... Now, where's my... Oh, yeah, where's the 2? Ah, okay. Yeah, so this isn't right. There's a value, and then the left child is a 2. And on the right is another tree. It's not a tree, actually. Let's see the directions again. Yeah. Each node contains a value and a list of child nodes. Yeah, so they are the child nodes, so the value is 2. Left is nil. Ah. And the right so does that make sense? Yeah, I guess that... Okay, it does make sense. Cool. And the right is just 4. Alright, this makes sense. So let's say I'll just evaluate this. That's our tree. Now, yeah, to get to the 1, we do need to go... Let's see what the JavaScript one is doing with the left function, because I have a feeling that it's not the same as... It's not a navigation function, is it? Let's see. So, left... returns a new zipper. Left. Right. Value left. Left. Value right. I have no idea what this means. Set left and set right. Rebuild tree. From tree. I wonder if there's a different language that's not object-oriented that I can look at. The problem is I don't know Haskell very well, but it might be a better one to check because I hate this constructor bullshit. I literally just have no idea what it is doing. Ah, so it has the zipper exercise. Let's cool. I hope it doesn't use monads. Binary tree, zipper, from tree, to tree, value left, right, up, set value, set left, set right. A binary tree. Ah, yeah, this uses stupid monads. Maybe. Maybe not. Stores the history of how the focus was reached and the value and other paths higher up in the tree. The history of how the focus was reached. Wow, so that's what the trail is. I didn't realize it took the whole history of how we got there. Okay, so left gets the left child. Okay, so yes, that actually answers my question. We just want to return the child. We don't want to do any navigation. But if we do want to actually go down into the zipper so that now the value is 1. The parent nodes is the whole thing. So to the right we have that. Okay, so something, I think this is not right. On the right, we need to go down again in order to get to where the child is, right? We go down, down? No, because then we have nothing. Let's see. What if we go to the right? No? What if we go right before going down? There should be nothing there, right? Yeah, that makes sense. This is so... I don't know. I'm wondering if I'm confusing myself like royally by trying to reconcile two different implementations. Probably. Let me look at the Haskell one some more, because that was cool. This is it. This is the Scarlatti. I love how just perfect and mechanical it is. And it's slower. I might have slowed it down. I want one of those little tiny harmoniums like Stewie was playing on Family Guy. Did I say harmonium? I meant harpsichord. I'll show you what I mean. Let's see if I can find it. Stewie... Yeah, Stewie Griffin... Mozart? Maybe? Yeah! Let's see. On piano... Family Guy powdered wigs, Stewie on piano harpsichord. Stewie becomes Mozart. Yeah, this is it. Okay, I'm gonna fade this out. I've got my audio compressed. That's why it's like not fading stuff out properly. But yeah. Oh, you know, I can't show stuff like this, or it's gonna copyright strike me. Anyway, I guess it doesn't matter. I just wanted to show the little toy harpsichord. Isn't that so cute? I want one. I was just thinking about getting some sort of piano today. I should get like a little harpsichord like that. It would be all right. Fade. I'm going to turn my compressor off and watch. I'll fade the music back up. And listen to how smooth this goes. Oh yeah, left and right are supposed to get the, so if we're not moving at all... yeah, so... I don't actually know if I'm representing the binary trees right, because... Oh, no, this is my grandma playing Chopin on the piano. So we can't go right, that doesn't make sense. But we can go down. Yeah, where's our 2? And what happens if I try to go right? We get nil. Why would that be? Because it's checking for siblings. No. this is trying to move right. What's that? Oh my god, this is annoying. I don't know. I don't know how it's supposed to work. So I thought there were supposed to be functions for moving around. Get the lift. I think... I suddenly don't like zippers so much. I probably would if I understood how this is supposed to work. I mean, maybe we should read the paper? First, let us present a version which pertains to trees with variadic arity anonymous tree nodes and tree leaves injecting values from an unspecified item type. So you could use a zipper to make a text editor. That would be fun. First I have to understand how the hell they work. The basic idea is simple. The tree is turned inside out like a returned glove. Pointers from the root to the current position being reversed in a path structure. The current location holds both the downward current subtree and the upward path. All navigation and modification primitives operate on the location structure. Going up and down in the structure is analogous to closing and opening a zipper in a piece of clothing. Whence the name. The author coined this data type when designing the core of a structured editor for use as a structure manager for a proof assistant. This simple idea must have been invented on numerous occasions by creative programmers, and the only justification for presenting what ought to be folklore is that it does not appear to have been published or even to be well known. The mythological zipper. Zippity-doo-dah. We assume a type parameter item of the elements we want to manipulate hierarchically. The tree structure is just hierarchical lists grouping trees in a section. For instance, in the Unix file system, items would be files and sections would be directories. In a text editor, items would be characters, and two levels of sections would represent the buffer as a list of lines and lines as a list of characters. Generalizing this to any level, we would get a notion of a hierarchical Turing machine, where a tape position may contain either a symbol or a tape from a lower level. All algorithms presented here are written concretely in the programming language OCaml. Joy. The code is translatable easily in any programming language, functional or not, lazy or not. We have a tree. We now consider a path in a tree. A path is like a zipper, allowing one to rip the tree structure down to a certain location. A node, LPR, contains its list L of elder siblings, starting with the eldest, its father path P, and its list of younger siblings, starting with the youngest. So yes, Hue uses father instead of parent, so no problem. No. I'm thinking both the JavaScript and the Clojure implementations are both based on Hue, so I can't imagine them being too terribly incompatible. I'm still just wondering, like, can I make the zipper that operates on this? Like, can I... Can I make, like, a tree zip function? I mean, there's the XML one, for God's sake. zipper for XML elements as from XML parse. Yeah, see, so this is this was my first experience with zippers, which was, it was weird. I was trying to parse XML for a job interview, take-home project. Let me look up like Clojure zip tree or something. Map? No. Recursively traversing a map. Map zipper. This might be what I want. Inspired by the Clojure docs for Clojure.zip. That might be cool. Cool. Adds zip support for maps. This might be what I needed. Zipper. Let's see what this does. So we need my zipper function again. See, I messed up and hard-coded these. But it's okay, I'll get them back. Vector zip, blah blah blah. Branch children. And make node. Let's see how we use this thing. So here's a map. Treat nodes as key value pairs. Okay, where was the This was based on a Stack Overflow answer. Let's check this out. Clojure zipper of nested maps representing a tree. How can I create a Clojure zipper for a tree represented by nested maps where the keys are the letters? Could be that this is what we need. Represents a tree with two words, banana and Anna. Banana Anna. Banana Anna. I've tried to pass map vals assoc as three functions to the zipper. Map vals assoc. Map vals zip map would do, but doesn't support insertion removal of children. Since children are only values, you don't know which key to remove or add. I wish that made sense. It should. Oh, this was answered by Christoph Grand. Wow. The map zipper below does support insertion removal because nodes are key value pairs. Except the root, which is a map. Okay, nodes are key value pairs. How does that? Where the keys are the letters. Does that make sense for what we're doing? Function to leaf nodes. Nested maps were a tree with two words, banana, banana. And what are these $sign thingies? It's just like a nil. I guess so. Yeah, it just says, so A is like a leaf. And it's like, okay, that's it. And then, Anna. Anna. Okay. Oh. Okay, the solution proposed by Christoph Grant, it's Grand, is great, but implicitly describes a tree where all branches and leaf nodes have an associated value, the key in the dictionary, except for the root node that is just a branch without a value. So the tree, this /nil, is not a tree with a single leaf node, but a tree with an anonymous root branch and a single leaf node with value /. Neither of these made sense to me. In practice, this means that every traversal of the tree has to first execute a zip down in order to descend the root node. Oh. An alternative solution is to explicitly model the root inside the map. That is, only create zippers from maps with a single key at the root. For example, this. Huh. Define a zipper data structure to navigate trees represented as nested dictionaries. That's like exactly our problem. Is this the one? Okay, so which one of the... I think this is the one mentioned here. Yeah. This one works on maps too. Map vec zipper. Huh. Zippers with records. Make a zipper out of a tree. this tutorial, we use sequences as trees. A tomorrow tree. Cool. So let's try this. We won't do any editing. We need root. That's the end of that. Really? No more music? Down, right node. All right. So we have M. Or we have A is 3, and B has a tree, which is X, which is true, and Y, which is false. And there's C, which is 4. So A, B, and C. Cool. So that's actually fairly close to this heap, what we have here. So this might get us actually off the ground. If there's a value, a left and a right, let's see, how does this correspond? We can see how this works. Note that hash maps are not ordered. We know that. Thank you. So we have B. Yeah, because we've gone down, right, and then printed out the node. Where's map zipper? We need to so the branch predicate a map can be a branch if it's either a map or if it's first if the second element is a map. So let's show how this would work. So let's say then we have M, which is our whole thing. Okay, so that doesn't make sense. M is a map, so we know that it's a branch. I want to play some Scarlatti or something. I actually might need to stop streaming and eat something. Yeah, I think I might do that. It's been like 4.5 hours. And yeah, I didn't get much done this stream. We're mostly just complaining about how I don't understand zippers. And got a tiny bit closer. Mostly just like got a lot of respect for these hard problems. Okay, so yeah. Well, you know, it's gonna be lonely. I'm gonna miss y'all when I'm gone. Well, see you later.